Unit 4 Review, Problem 3. The total stopping distance in feet was measured for a mid-size four-door sedan driving in dry conditions at various speeds. The resulting data are presented in the table below. Part A asks, determine the linear regression model that will best predict the total stopping distance for a mid-size four-door sedan traveling in dry conditions based on the speed of the vehicle. So part A is asking us to determine the linear regression model. So that means we'll perform a linear regression analysis. A linear regression analysis is used to predict one variable based on the linear relationship with another. So we can follow these steps to complete our linear regression analysis. The first step in the linear regression analysis is to enter the data. We have two data values, the x, or predictor variable, and y, the predicted variable. The linear regression model is the line y hat equals ax plus b, where x is the input data value, which is being used to make the prediction, and y, the output variable, is the one that we're predicting. So in order to enter this data into lists in our TI-83 or TI-84 calculator, we need to first identify which one is the x and which one is the y. The key is the one we're predicting. The variable that's being predicted is the y, and the y gets entered into the second list. So in this problem, we're asked to determine the linear regression model that will best predict the total stopping distance. So the total stopping distance data is our y, the one we're predicting, and that's the one that needs to be entered into the second list, list 2. X is the variable we're using to make the prediction. So in this regression model, we're basing our prediction on the speed of the vehicle. So the speed of the vehicle is our x variable, and it needs to be entered into the first list, L1. So now that we've identified which of the variables is our predictor data, x, and which one is the predicted variable, y, we can enter this data into our TI-83/84 calculator. We do this by pressing Stat and then Enter the editor. We could clear out the list 1 and list 2 of old data to make room for the new data. And in list 1, we'll input the x variable, in this case, the speed of the vehicles. And once we do that, we can then go to list 2. And in list 2, we'll enter the y variable, or the total stopping distance. Once we've entered all the x variable data into list 1 and the y predicted variable data into list 2, we can then use the linear regression command on the TI-83/84 calculator to calculate our linear regression model. The linear regression model is the line y hat equals ax plus b, where a is the slope and b is the y-intercept. And the command on the TI-83/TI-84 calculator that calculates the slope and the y-intercept for the regression line is the linreg ax plus b command. To get to this command, we press Stat, arrow over to the Calc menu, where we can calculate the slope and the y-intercept for the regression line, arrow down to the fourth option that says linreg ax plus b, and press Enter to select. And then next to the linear regression command, we need to tell the calculator the list where we entered the data. The first list is always the x data, and the second list is always the y, the predicted data. So in this case, next to our linear regression command, we go second 1 to bring up list 1, the speed of the vehicle, comma, second 2 to bring up list 2, which is our predicted total stopping distance data. Once we have our linear regression command with list 1, comma list 2, we press Enter, and the calculator calculates our results. So now by looking at the screen, we can write our answer to the question, let's determine the linear regression model that will best predict the total stopping distance for a mid-size four-door sedan driving in dry conditions based on the speed of the vehicle. So the answer to this question would be that the linear regression model is y hat equals A, calculated by the calculator, is 6.42. Here the data, the speed, was whole numbers only. To make our prediction, we need to carry at least one extra decimal than that for round-off error purposes. But this isn't our final answer. We're going to use this rounded off number to make a prediction for the other rounded off number. So we need to carry one more than the one more decimal place that's needed in this problem. So we're going to round off the slope, to 2 places after the decimal. So we look at the third place after the decimal. It's a 0. Anything that's below the 5, we just round down the answer, in this case, to 6.42. So the linear regression model is y hat equals the slope of 6.42 times x plus b. The calculator calculated b, the y-intercept for us. Here, b equals negative 70.0357. Well, b, the y-intercept, is a negative, so we don't write this as plus, we write it as a subtraction. So we write this as minus 70.0. And again, we need to carry 2 places after the decimal in this mid step in order to give us 1 extra place after the decimal of accuracy in our final answer. So the 5 in the third decimal place is 5 or more, so we round the 3 up to a 4. So the y-intercept is written as minus 70.04. So now we have our answer to part A. The linear regression model is y hat equals 6.42 times x, subtract 70.04. Now we could answer part B. Part B asks, how well does the linear regression model fit this sample data? Well, in our linear regression, we look to the coefficient of determination, that is the r-squared value, to determine whether the regression model fits the sample data well or not. The idea here is that the coefficient of determination, r-squared, whenever it's very close to 1, fits the sample data very well. But when the coefficient of determination, r-squared, is close to the 0, it means the regression model does not fit this data very well. So here we could see on the calculator that the r-squared is equal to 0.981. And since the coefficient of determination, r-squared, which equals 0.981, is very close to 1, we can conclude that the linear regression model fits the sample data very well. The closer r-squared is to 1, the stronger the relationship, and the better the fit of the model. The closer r-squared is to 0, the weaker the relationship, and the less well-fitting the model is. So here's our answer to part B. Since the coefficient of determination, r-squared, equals 0.981, is very close to 1, the linear regression model fits this sample data very well. Now we can answer part C. Part C asks, predict the total stopping distance for a mid-size four-door sedan driving at a speed of 65 miles per hour in dry conditions. So here we get to use our actual linear regression model to make the prediction. That is, we're going to take the y hat equals to 6.42x minus 70.04. We just need to plug in the input value for x. Here, x in our model was the speed of the vehicle. So the speed of the vehicle was the 65 miles per hour. Plugging that into the regression model, x equals 65, we get y hat equals 6.42 times the x of 65 miles per hour, subtract the 70.04, and we could press enter. Here we get 347.26 for our predicted y. And y in our model is the total stopping distance. Total stopping distance is measured in feet. So for x equals 65, that is a mid-size four-door sedan driving at a speed of 65 miles per hour in dry conditions, the total stopping distance, y hat, equals 6.42 times 65, subtract 70.04, equals 347.26 feet. So now we can give our answer to part C. Thus, the total stopping distance for a mid-size four-door sedan driving at a speed of 65 miles per hour in dry conditions is predicted to be 347.3 feet.